Webinar where I'm going to talk about quantification of clean steel. My name is Patrik Ölund. I really like talking about clean steel. I've been working at Ovako for 25 years, working a lot with this. I'm heading the department of R&D and one of our tasks is really working with this. I have made some kind of agenda for today, talking about the background, sort of why do we really need to quantify clean steel, the starting point. Then moving over to the limitations that we have with current standard. We believe that we have a very hard time, or everybody has a hard time to really quantify the steel today and get a fair understanding of how it will perform in a real application. Then moving over to what we see as the improvement we can do, that we actually do today, that we are working on today in the laboratory, actually to fine-tune our process and develop our process to make even cleaner steel for the future. Which is something that we think has been a great potential, even though we have been working on for such a long time. We really now see equipment and things like that are all falling into place, making it much easier to analyze the data and much better equipment to use. We would like to see this kind of techniques more used in the world. We know a lot of the companies today are looking into this and working with this, and we are working together with bigger companies with this as well. But we believe it could even expand more. I will summarize this, and then we have a question section, so please write in the chat. Now I see you can hear me. That's good. I don't know what happened. We will then answer, or I will answer the questions in the end of this session. So please write it already if you have, and then I try to summarize. And the one that we don't really have the time to answer today, we'll of course answer per mail. And I know that Anna will actually put them also perhaps on the special Q&A that she can link to on the next newsletter that will also be about quantification of steel, sort of a follow-up. Then I have some end remarks just to try to wrap it up, and I think that's it. I'm not alone in this. Strong development requires strong teams, and we have a really strong team. You can see the individuals here working very much on this in different ways and different levels. With that said, we are not limited to these numbers. We have a fantastic cooperation also with our mother company and sister companies in Japan, Nippon Steel and Sanyo Special Steel. We are working on this together as well, and they are really good, because you really see that putting all these resources together, the thinking, the critics and everything makes it really good, and we have a very fantastic cooperation together. So now I will move over to the real stuff, talking about quantification of clean steel, and starting with the question. In a short while, I just need to go and fix the thing. Since I fixed the sound, I need to also do like this. Now I can use this one, and then we will try to answer the question, why do we need to quantify non-metallic inclusion in steel? And there could be several reasons to this. I think the one that I will move more into is the first one, the fatigue properties, because we know that fatigue is causing the majority of the material related failures in the world is actually due to material fatigue. And that's why we really need to, I've heard numbers up to 90% of the material related failures. So it is really important. So that's what we're going to focus on. But of course there are other possibilities. We talk machinability, to find the right kind of inclusions to really aid the machinability. We know chrome plating. In order to chrome plate or coat something, you also would like to avoid having surface defects in form of inclusions, and you can use it for that. For surface finishing, polishing, polishability and things like that, and toughness. And there are more things that we can do. But fatigue is important. It will cost the society a lot of money. It will lead to an early failure. It's not very sustainable. We want to be sustainable. We want to make material that really can do the job for a long, long time. And then we want to limit this. So, how can we do that with clean steel is the next question. Yeah, we know for a fact that the fatigue strength of a steel can be very, very much influenced by the presence of non-metallic inclusions. Normally the strength or the fatigue strength of the steel, you could say, is divided into two different things. Either it breaks due to the strength of the steel itself, we call it the matrix strength, or the intrinsic fatigue. I call it intrinsic fatigue here. And the other one that really takes it down is if you have some kind of defect that acts as a stress raiser, and that will cause the fatigue earlier, because then you will surpass this strength locally around the inclusion. As an example, if we have a material that is around 400 Vickers hard, the intrinsic strength is very, very strongly correlated to the strength, and the strength is very correlated to the hardness. So we use that hardness. It's a simplification, but it is fairly good to do. So we know that if you have a 400 Vickers component, you will actually have a fatigue limit somewhere around 650 or something. And we know that you can actually allow then an inclusion that is down to 20 micron. If you have a bigger inclusion, then that will cause the failure and not the matrix. So it will go from 400 downwards. But as you see, the slope is pretty slow there. So it's not a very dramatic effect. The big drama comes when you have high strength steel, and that's what we normally have in bearings, gears and things like that. Then you are on this side where you have the very, very steep slope. And then you see, as a matter of fact, you can, in a 700 Vickers hard steel, theoretically, the intrinsic strength is somewhere around 1150. But you very rarely see that. You can see it, and you do see it if you test a very, very tiny material volume. If you have a very, very small gear with very, very small teeth and you stress a very small volume and the surfaces are perfect, then you will end up here. But no longer, then will break. But if you start to get inclusions in it, you see that once you get inclusions that are above 10-15 microns, you will get a reduction in fatigue. So this is why we don't like these ones. These ones are the ones that we want to avoid to get into our customers' stressed volume. So we really target the population, let's say from 20 microns or perhaps 15 or something, but in that region and upwards. That's where we want to have the knowledge about how steel looks like. So this is the problem. We are really looking for a needle in a haystack. I think it's literally exactly like that. We are looking for something that is quite rare in a volume that is fairly big. And this challenge us to find methods that are perhaps a bit more innovative than we have in the past. Because in the past we have used methods with small volumes or small areas. But if you start to look, and now we made some investigation, this is a test we made. This is a test we made when we looked at our fatigue specimen, looked at each individual failure, found the size of the inclusions, and we knew how big volume we stress. And by plotting this together, we can get an idea, or we can get a measurement of how many inclusion of a certain size that is likely to find in this steel. And combining that also then with other methods, we can start to get sometimes what we call the true inclusion distribution, which is much more also about the larger ones size population. This is an example we made, and we made a lot of tests on the 52-100 steel mainly to really get an understanding the true inclusion distribution. And how does that really look? And how does that really vary between different material qualities? We have seen this, and this is not exact figures. It is as estimates, but they are realistic. They are at least tested, and we see this if we test our samples that it's in its region. If we look then, make a table here with the size ranges that we have, and how many inclusions would you expect per liter steel in the different size ranges. And then I divide it by clean steel and what we call then standard steel, or not that clean steel, to be honest. And this is made on the globular non-deformable oxide inclusions, the ones that we find on the fatigue specimen and so on. And as you see, in 1 liter of steel, you find an awful lot, you can say. 30,000 of inclusion that is between 10 to 20 micron in a clean steel. Yeah, that's what it is there. But on the other hand, you have 100,000 in a non-clean steel. I mean, these ones are not on the really most dangerous part. The ones that are dangerous are the ones that are around 30, 40, 50 microns. And you see there you have 30 or 300 compared to a standard steel that you have 5,000 or 10,000. Quite a big difference. So we want to capture that. Today, when we rate steel, we use very often light optical microscopy. Light optical microscopy involves that you look at sometimes 6 samples, sometimes less. This is a sample. I have a small sample with me. It's an area that is around 160 or 200 square millimeter. And we sort of looked at that, tried to find the biggest inclusions, and then we are trying to get an idea of how it looks in 100 tons. I mean, in the best of world, everything would be normal distributed, or you can actually extrapolate, but it's not really like that in steel. It is very difficult to interpret or to predict what you see here in a big volume. I made the same table. I just made some assumptions that actually what we see here is not an area. I say it's a volume, just saying that we should, when we polish it once, we could see a depth around 0.1 millimeter, which is quite nice to this test method, because I think it's less, to be honest. But if you look at that, you see what is sort of the probability of finding a defect of a certain size in this. If you remember a clean steel, you can find in 1 liter it was 300,000 of this one. And you can see here, it is below 1. So you need 3 samples of this in the clean steel to find one that is 10 to 20 microns, which is normally what you are experiencing as well. You might find one in a non-clean steel. But this means that actually the information you get here is so limited. To predict something from these values, 0.3 or 1, is sort of the normal case, but you can have zeros in both, or you can have ones in both, and you cannot really judge whether this steel is better or worse than the other. So this is really the problem. What we are doing is we are looking at two small areas to be able to really predict the real cleanliness of the steel. So, because when we then look at, so if we look at what we rate on a standard sample, it's 100 cubic millimeter. If I'm very, very generous with the method, I say it's 1000 plus times 0.1 millimeter, which is very few components are that small. Very few things that we use in our industry or in our applications are that small. It could be very, very small, the smallest type of gears and bearings, perhaps tiny things, then it becomes. Normally you have much larger components. So for instance, if you have a component that is around, where you stress around 1000 cubic millimeter, you have that is a stressed volume where you put some reasonable stress. Then you say, if you look at the E45, I hardly see any difference. But if I test it and start to test it, I see actually that in the clean steel, it's limited by inclusions that are 20 to 30 microns perhaps, because there you have 3 of them. While in the non-clean steel, perhaps it's around 40 to 50 micron, that limit. Which means, if you looked at the graph before, you will actually expect the fatigue limit to go from 600 to 400 megapascal. But you couldn't see that in the normal rating. Which means that rating is more or less saying everything is within some limits, but it doesn't really tell you how good it is. So what we are working on is trying to find improved quantification techniques. And there is no shortcut here. There is no way of really making it easy. I mean, you can use extremely advanced statistics, but if you don't have the data, you will never predict anything reasonable. So you have to look at bigger areas and preferably look at bigger volumes. So what we are working on is very much microscopy of large areas. We've done that for a long time. It is a very powerful way of doing it because you can actually get the chemical composition, you can get a lot of knowledge about it. Well, then we start to look at these kind of samples instead. Considerably larger pieces of sample, looking at the several, and then you get much more information as well. So that's one thing. We are also working with fatigue testing, of course. It takes a lot of time to break these ones into two. But it's a powerful thing because then you see, yeah, that was the biggest one here, and we can actually go down and we can analyze that as well. So it's an excellent. But we also now see the opening of working much more with immersed, very high frequency ultrasonic testing. We've been working with that for a long time. We have a very good method with 10 megahertz, taking a good way of discriminating between larger defects. We have that published on our website as well, so anyone can use it as their specification or standard and use that for sorting out. But we have now much more advanced methods as well. Immersed high frequency ultrasonic testing. And now we start to look at these kind of things. This is a sample for 25 megahertz. And yeah, the area is big, but the big strength is that you look at the volume. So you look at an actual layer here inside. That is around, depending on what method you use, but it's a considerable volume that you use instead. And then you start to get some data, some real data. The first one, the micro inclusions with SEM, but I talked. We can then start to see differences in the range of 10 to 30 microns. There you start to get, if you start to look at bigger areas. But we are still not really seeing the ones that are bigger. But this is an excellent method. It's an excellent method of assessing these kind of inclusions, and it's also giving you or providing you with information when it comes to chemical composition. We can understand the origin of the inclusions as well, which means that it's very, very powerful also for our process development. This is an example when we actually rated 2 different steel with this, so the same kind of grade, but from different sources, where we used continuous cast conventional steel, what we call this, the standard one, and compare that then to an ingot cast bearing quality steel in this case, and then you can see that you will get a quite big difference in number, despite the fact that on an ASTM or ISO rating, these ones are fairly similar in quality when it comes to that. So moving over then to the high frequency ultrasonic, which I think is really something that we will see more of also in more regular testing. We use this kind of equipment, which is quite small and very controllable. But we also have equipment out in our factories. When we do today on a standard or a regular basis, we can do 10 megahertz testing, which is a very powerful way of also looking into a process, noticing if you see any process changes and things like that. But here we are moving higher. We are moving from 25 up to, I would say, 125 megahertz is what we are testing. And you can see here, the picture is actually C-scan, they call it. We call it. It's actually one piece with a perfect defect in it, and what you see is all the layers stacked in of the volume. So you see actually volume then compressed to an area, and you can see that defect, the smallest defect you see here is 50 microns. So if it's a perfect reflector, we can see down to 50 microns, which is quite good, and then you start to get that. And you remember that volume is huge comparison. So, and what we've seen is actually we do have a good correlation between fatigue now and these kind of more advanced methods. We can, if we look at the SEM method that we have up there in the corner, we can actually see that on some different steel that we produced and tested, we actually have a correlation with what we find in our index that we use there, the number of defects larger than a certain size, and the fatigue measured with our rotating bending in this case. The rotating bending also correlates with when we do a rapid testing with 20 kilohertz testing, just to find, and just trying to find the largest inclusion. So this is also a way of using it. Quite interesting method itself. And very important, we see also the 25, which is the foremost, fastest and easiest way of finding here. We do have a good correlation there as well. As you see here, we all tested extremely clean steel. We are talking about fatigue limits of 1000, 1100, which is sort of very high up. And of course if you start to look at a less clean steel, that value would be much further away from this, much lower in fatigue limit and much higher in. We haven't completed those tests yet, but that they will come as well. So this just encourages us to work with this 25 and higher frequencies. What we are doing is we are also ongoing the development of working with 125 megahertz. This is extremely high frequency, but also frequencies in between. And we see there that it's possible to detect defects down to less than 20 microns. It's even possible to see and detect sulfides. So this is just an example of something where we looked at. So this is just a model material that we have. It become extremely clear. The defects that you have in that is 50 micron, they are very easy to see. So that was the limit for, remember, that was the limit for 25. Here it's sort of extremely easy to see. But you can also see, as you see here, sulfides. It's a comparison between a sulfurized steel and a non-sulfurized steel, 52-100, 100 chromium 6 steel, which is both good and both bad. We want to quantify, but it's the problem is you cannot see on the ultrasonic if it is a sulfide or an oxide. So you have to put them together. And that's also a challenge. So we have to also work with the understanding of the sulfur content, how much sulfides that we have. So it's both something good, but it's also something that can also cause some difficulties. Really exciting. We're working very much on this, and we believe that we will have quite good use of that, both for process development, but also perhaps in our understanding of our products and our offering. So what we see with 25 megahertz, we believe that we will start in the future, or already now. This is what we do today. The 25 is what we do today. We rate from 50 microns and upwards, and we can really get that kind of knowledge. And this is work in progress, but we are heading quite rapidly there as well. Very interesting area, and we do see a lot of interesting observations as well. So our way forward, how we see it, how should we work with this? Yeah, we would like to develop these improved quantification methods, and we need to have the sufficient volume. That means if it's smaller volumes that have a higher frequency, we can actually allow for looking at smaller volumes or even areas. But if you start to have the larger ones that are more rare, you have to look at bigger volumes. And I think that's one reason why we can combine several methods. The reason why that is, it's really important and good for us. So working here with the SEM or light optical microscopy for the smallest one, giving us good feedback for the steel mill as well, and giving sort of the knowledge about that size. Using then the 50 to 125 megahertz to fill the gap where we can take it with the 25 megahertz. And then we have a true distribution. We sometimes call it a true distribution. And I think our way forward as well, and we talked about this, when we have that, we can do this, we will also have the possibility not only to feed to our own process to make improvement, but also supply our customers with that kind of data. And perhaps then we can have more a fatigue calculator. You can actually take the data we generate by this. We can understand what is the true inclusion distribution. And using that and the known stressed volume in the component and how it's oriented because that will also influence. And in total, you can actually then compare different qualities. And of course, that depends on how clean you make the steel, how much you process the steel, roll it down and break up, because that will also change the true inclusion distribution. So it's a lot of work, but it is a fascinating and it's a feasible future, I believe. So this is our way forward. I spent a lot of time, but a lot of time also checking that the sound was okay. So I hope you're still with us, and I will then move over to the questions, and I will see if there is any questions coming in. Let's have a look here. Now I have the live chat in front of me. There is no sound. I heard that. That was. Meanwhile, I can I can just answer a question for myself. I mean, we also talked very much before about oxygen content. We have also looked at that quite much, and that is also a strong indicator that we are using, and it still will be, but we know that it's not that alone. It's also how the oxygen is distributed and how the inclusions look like after the. So this is something that we are keep on doing. Oxygen is still important. It's a measurement that we are following very carefully, but it will also need to be combined with how the oxides look like in the product and the size distribution. I have some questions. We'll start with some from. The question is, will these methods be adopted by international standards? Yeah, that's a good question. My experience that international standards are quite slow to influence, but we do have the ambition to work with that, to get that into standards, and depends on the time frame. I would say I will definitely see this in the future, yes. But if you talk about a couple of years, I think it will take time. We've just started this journey. It will probably take some time to get it there. Yeah. Thank you, Andrew, for the question. So, if that's all, then I will end with this. And if you have any other questions, you are welcome also to mail, to contact. And as we said, we will have a next strength of steel will actually cover this, and we can actually use those questions for that. I have one thing more to add. It is that we also have some end remarks that I have. The international standards, that gives very small information. I think that's a fact. We have to live with that, and we have to find new ways. I think that we have tools with the high frequency that we have, and I believe that starting to talk in terms of true inclusion distribution will be very, very helpful in understanding how to select steel for a certain application. I mean, with that said, I mean, if you have a very small stressed volume, to be honest, it's not as critical to go for the very clean steel. Vice versa, if you're going to have an increased volume, it becomes much more important for the clean steel. But this understanding is important. Today we just rate the same steel from a billet, and we don't know how it look like in your end product. Okay, I will then just wrap it up with presenting the coming webinars as well. We will have it the 9th of February. It will be about sustainability, carbon neutral now, our initiative, which is great. I hope you will join that. And then 17th of February we also have machining guidelines, how you machine our steel. So I just have a quick look here. No more questions. I will then just thank you for participating. I hope you stayed on despite the problems with the sound there. But thank you for participating, and have a good rest of the day. So thank you and bye.